Hey class, today we are going to move on from acid and base theories and acid-base reactions to determining pH and titrations. This is going to be chapter 15, section 1. We are going to do these objectives. We're going to describe the self-ionization of water, define pH and give the pH of a neutral solution at 25 degrees Celsius. We're going to explain the pH scale. Really, the big part of this video is going to be determining hydronium ion concentration or hydroxide ion concentration. We might even get into pH in this video. All right. Also, by the end of this section, you're going to be, if you're given the pH, you'll be able to find hydronium or hydroxide ions, whatever their concentration is. All right, self-ionization of water. Two water molecules produce hydronium ions and hydroxide ions by the transfer of a proton. So what does that basically mean? Is water has the ability to self-ionize. It will react with itself. So say this water right here, it will donate its proton, that's your Bronsted-Lowry acid, to this water, which will accept it, that's your Bronsted-Lowry base. So in the end, after this donates its proton, it becomes OH minus, your hydroxide ion. Once this accepts it, it becomes hydronium. So water will self-ionize. It will exist as hydronium and hydroxide ions combined together. Equal numbers of each. In a pure water at 25 degrees Celsius, the hydronium ion concentration is 1.0 times 10 to the negative 7 molar. The hydroxide ion concentration is also 1.0 times 10 to the negative 7 molar. So for pure water, they are exactly equal. So the equation for the self-ionization of water is Kw, that's a subscript, is equal to the hydronium ion concentration times the hydroxide ion concentration. So you take that with 1.0 times 10 to the negative 7 molar times 1.0 times 10 to the negative 7 molar, you will get 1.0 times 10 to the negative 14 molar squared. Okay, so that becomes your equation. So it's a self-ionization of water. Now, you can tell if any solution is neutral, acidic or basic, by the amount or concentration of hydronium and hydroxide. Hydronium is, if it's 1.0 times 10 to the negative 7, and it's equal to hydroxide at 1.0 times 10 to the negative 7, your solution is going to be neutral. If you have a higher concentration of hydronium, now it could be a little confusing, it's 1.0 times 10 to the negative 4, that is much larger than 1 times 0 times 10 to the negative 10. Each of these are a factor of 10, so much larger hydronium ion concentration, so that would make it acidic. Now, hydronium, if it is 1 times 10 to the negative 10 molar, that would make it much less than the hydroxide ion concentration being 1.0 times 10 to the negative 4 molar. So in this case, it's going to be basic. Okay, so whatever is the highest concentration determines if it's acidic, basic, or neutral. All right, so at 25 degrees Celsius, Kw is equal to the hydronium ion concentration times hydroxide. This is your equation for Kw. And at 25 degrees Celsius, for pure water, it's 1 times 10 to the negative 14. All right, it does change with temperature. Kw increases as temperature increases. So everything we're going to be talking about in this particular section is going to be at 25 degrees Celsius, because that Kw will change. You'll see how it increases as the temperature goes up. We are focused on this temperature. All right, monoprotic and diprotic are very important when it comes to calculating hydronium ion concentration. In this case, you have, or hydroxide ion concentration. In this case, if you have 1 mole of sodium hydroxide, it will dissociate and give you 1 mole of hydroxide. So in this case, that would be considered monoprotic. So if you have 1.0 times 10 to the negative 2 molar NaOH, then we can do the calculations. It just basically means that if for every 1 mole of this, you're going to get 1 mole of that. We can show the math why that is, 1 mole of OH. So that also becomes your moles of hydroxide. So that's the moles of your sodium hydroxide. That would be your moles of hydroxide because it is monoprotic. Now here's a diprotic acid, H2SO4. You can see what happens here. For every 1 mole of this, you're actually going to get 2 moles of hydronium, if you look at the coefficients. Since that happens, then let's go through the math of this. 2 moles of hydronium for every 1 mole of sulfuric acid. That will give you twice what the moles of sulfuric acid is. You'll get twice the moles of hydronium. So diprotic will do that. If you have a triprotic, you're going to get 3 times the amount. So it's very important to recognize if you have a monoprotic, diprotic, or any polyprotic version of acids or bases. All right, so in this case, you're going to get 2.0 times 10 to the negative 2 moles of hydronium. All right, so calculating hydronium and hydroxide, strong acids and bases are considered completely ionized or dissociated in weak aqueous solutions. So strong acids and bases, in this case sodium hydroxide, it will completely form hydroxide ions. So your concentration of NaOH is going to give you 1 mole of OH minus. So if we have 1.0 times 10 to the negative 2 molar NaOH solution, it's going to have a hydroxide ion concentration of 1.0 times 10 to the negative 2 molar. So how do we determine the hydronium ion concentration? We're going to use our Kw equation, our self-ionization constant, which is 1.0 times 10 to the negative 14. So we know the hydroxide ion concentration. We know the value for Kw at 25 degrees Celsius. So we can solve for hydronium ion concentration. So you just divide both sides by the hydroxide. You're going to end up with this equation. Let's put the value in for your hydroxide, 1.0 times 10 to the negative 2. It's an easy calculation. It's just going to be 2 off of the 10 to the negative 14, so 10 to the negative 12. You can use your calculator for this. It's very easy, but you can also, you can generally do in your head. All right, so if you have the hydronium ion concentration in the solution and the hydroxide ion can be calculated, you can also use Kw. HCl, we know it's monoprotic, so we know our hydronium ion concentration is going to be the same. Use our Kw equation, 1.0. We're going to divide both sides by this time by hydronium. Replace that with the concentration for hydronium, and we will get, now we have to use, since it's 2, now you should use your calculator. It's not as easy to calculate. It would be 5.0 times 10 to the negative 10. So a low concentration of hydroxide. Here's some strong acids and weak acids.